Edwards, and I'm the Dean of the Inamori School of Engineering, and it is my pleasure to welcome you to our annual McMahon Lecture. Before I get started with introductions, I'd like to take care of some housekeeping notes. For those of you who signed up for the McMahon Luncheon, it will be in the nightclub in the Powell Student Campus Center. So just follow the trailing folks when the lecture's over. And also, we're going to have several tours of the engineering facilities. And so if you're at the luncheon and you're interested in tours, just let us know when you're at the luncheon and we will organize the tours from there. At the McMahon Lecture is a time when we introduce and recognize the accomplishments of our students who are involved in the cooperative education program. And one of these awards is the McMahon Achievement Award. And it is my pleasure to make this award to Ms. Diane Latar. Diane, please join me. Before I give Diane her award, I'm going to tell you how wonderful she is. So, Diane is really I call her the poster child for co-op and experiential education. How many co-ops have you had? How many internships? 2 in her short time here. So most recently, she worked for CesaRano, and she's a senior major in ceramic engineering. And with her co-op in CesaRano, her supervisor, Jordana Paul, who's also an Alfred graduate, said, "Diane has shown herself to be intelligent, hardworking, and engaged in her project. We have put her into a position of conducting the majority of laboratory work for developing a new beta-aluminum ceramic battery membrane. She has taken on the challenge of conducting experiments to help CesaRano develop tape casting methods for the challenging material system, and we are so pleased to have Diane as our co-op student." And I should also mention that Diane was my boss during her time at CesaRano because she actually contacted my lab to do some work. So that's quite funny. So maybe funny is not the word, but it's funny. So I'm happy to present this award to Diane. We're going to get over here so that Emily can get some pictures. And and that is a gift card, and so please use a wallet. So thank you. Our second award is called the Robert R. McComsey Career Development Award for Outstanding Co-op Award, and it is presented to Avery Chase. Avery, please join me. And we're going to do the same thing. We're going to say embarrassing things about Avery, right? Not actually embarrassing. Avery's a mechanical engineering student. He is graduating in December. He worked as a co-op student with Cummins. His supervisor, Jim Beersford, said, "Avery has a great work ethic, initiative, and is eager to work on projects large and small. He's not afraid to get his hands dirty, and he pulls his weight by example, and he's keen to learn more. He's demonstrated good practical mechanical skills, and it's been very helpful to our environment. He was a big help in our group here at Cummins. We appreciate the help for our business and likewise hope that his experience has helped him grow in his knowledge in mechanical engineering. We like Avery so much that we offered him a job, and he subsequently accepted a position of lab operations engineer here at Cummings in Jamestown within our test service group. So, Avery, it's my pleasure. Ceramic engineering and the McMahon chair in ceramic engineering. So the chair is the division and also the McMahon chair. So I turn it over now to Dr. Party.
Good morning. One of the jobs that I have as the McMahon chair is to select the McMahon lecturer every year. This year, it's my pleasure to introduce Joe Cesarano. Joe Cesarano is an alumnus of Alfred University, graduated in 1983 with a degree in ceramic engineering. He received his MS and his Ph.D. from the University of Washington, and that's where I first met Joe. Joe and I had the same advisor, and that probably requires a different conversation. Joe worked on colloidal processing. So if you had my ceramic engineering or processing course, you're familiar with his paper, Polyelectrolyte Stabilization in Aluminum by Cesarano, Oxide, and Blyer. He's the Cesarano. Okay. It is probably the most often cited paper in ceramic processing, a landmark. So after leaving the University of Washington, Joe went to work for Sandia National Labs as a researcher, and then in 2007 he split from Sandia to form his own company called Robocasting. So it's my pleasure to introduce Joe Cesarano and his lecture today, the John and McMahon Memorial Lecture.
Thank you, Bill. Is it too close? Whoops. Okay, well, Bill, thank you very much for the introduction. This is quite an honor for me to be able to give this lecture today. I know how important it is being in those seats when I was your age, hopefully not sleeping, but sometimes sleeping through the lecture. I'll try not to do that to you today. So I want to start out with talking a little bit about Alfred University, because it's had such a profound influence on So, anyway, Alfred basically, when I came here, the only program they had was ceramic engineering. So that's what I studied. I wanted to be an engineer, and that's what we did. Ceramic car engines were going to be a thing of the future, and 40 years later, they're still a thing of the future. But regardless, I want to take a second to acknowledge some of the, listen to some of the people that at that time, ceramic engineering was in its heyday, and the professors here. We didn't realize it at the time, but you look back now, we actually had like a Hall of Fame. This was like the New York Yankees of instructors for ceramic engineering. And Professor Burchett, he organized the study abroad program, which I participated in and did 8 months in Germany. Professor Pye is a world-renowned glass scientist. Professor Burdick, who's in the audience today, was a great instructor. Professor Tuttle for electrical ceramics. Professor LaCourse, who I had breakfast with this morning for glass. And Professor Johnson taught us mud lab and how to get our hands dirty, really understand ceramics. And Professor Barner, who's also still here. Some of these guys are still here. And Professor Tinklepaw. And then there's some other people too. Professor Rosington, Professor Brownell, and Professor Webb, if people remember the names of the physics department, made things so difficult that in order to pass this class, you had to get a 10. And in order to get an A, you had to get 40. So, I mean, this was unbelievably difficult stuff. But now I understand that after having it for 3 classes, what it basically instilled was that you can tackle difficult things. And gave you the confidence to do that. But of all these people, there's really 3 that stand out in my mind as just being unbelievably influential for me. And one is Professor Les Bentz, who taught chemistry and probably is the most talented chemistry teacher ever. Really. And again, one of these guys that maybe had an unbelievable talent for making difficult things or things that seem to be unattainable, understandable. Give you the confidence that you really could do something that was beyond what you thought your capability was. And then also Professor Jim Reed, who was a ceramic processing person and big influence on my career. And the thing that probably before today, the most exciting or meaningful thing in my professional life was when I read Dr. Reed's book on ceramic processing, which is sort of like the Bible of ceramic processing nowadays. And there's a couple of pages describing my graduate work in that book that he felt was useful enough to publish. And it's just blew me away that would happen. And lastly, Professor Jim Funk, and I don't know how many of you know these names, but he's no longer with us. And he didn't have his doctorate, but what he had is years and years of ceramic processing experience. And more than that, he had the intuition and the wherewithal, the forethought to understand that to really understand and to do creative things with ceramic particles and to turn them into beautiful products, you had to understand colloidal chemistry. And he was the one that introduced some of us in elective classes that understanding the interparticle relationships of these tiny little particles. And nowadays you call it nanotechnology, back then we call it colloidal science. That's how you really could tailor what you needed to do to make a creative or innovative ceramic product. And I took that and ran with it in graduate school and took that path of trying to understand colloidal science as much as possible. That was a new thing back then. Ceramic integration, you do that. You mix things and you study the effects of mixing things, but you didn't go down to the fundamental molecular level to try to understand this much. Now it's commonplace, but in 1979 it wasn't. Anyway, what I want to talk to you about, I don't have a lot of time, so I'm going to try to really go through this fast, or I'll just skip some stuff. But I want to give you an introduction into this concept of 3D printing with what we call robocasting. And the capabilities of the process. And then a little bit about the characteristics of the process, because there's so much hype on 3D printing in the last couple of years that I want to give you my perspective on what's maybe hype and what's maybe reality, at least to the state of the art today. And then lastly, some applications for 3D printing, particularly these lab stuff. So 3D printing, I think it's probably commonplace now. But when we started this work in the 90s, it wasn't. It's the idea of layered manufacturing. So instead of molding a part or machining a part, you're going to actually You're going to actually build a part. So you can make a CAD model of a part, then build it in a series of layers, and putting those layers together in some clever way so that you actually have some three-dimensional shape without ever machining or molding. Right? Regardless of how you do that, that's the bottom line. It's an additive technique. And 3D printing has sort of become a universal name to describe that, when in reality there's several different ways of doing that. The most popular method has sort of become the most popular method, is taking a plastic filament and then heating it as it goes through a heated nozzle, and then depositing that plastic in such a way that it's molten here and then solidifies here. And so these are all the plastic printers that you see out there. And the most popular one right now is the MakerBot. And MakerBot, you can make all unbelievably interesting, intricate, colorful parts out of different plastic materials. So they're really pretty and cool, but as far as technical applications, they're a little bit limited. But that's sort of where we're headed. Now there's several other techniques for doing metals and some for doing ceramics, but I don't want to take the time to go into that unless somebody really wants to at the end. What I want to tell you is the inspiration for my technique, or our technique, called Robocasting. And it's along the lines of ancient Indian potters in New Mexico and Colorado who would take clay and roll it out into strings and then coil that clay up, just layer by layer, until you got some sort of pot. So this isn't a new idea of how to make ceramics in layer manufacturing. It's several thousand years old. So if you look at a pot that's made like that, you can see the individual layers, but what you end up buying at the market, because they'll smooth this and then paint it, something more like that. But it's made by a layered manufacturing technique, it's just that it's done by hand. We're taking the exact same concept, but instead of using an Indian woman, we're using a robot. And so we have a CNC machine that will spit out a ceramic paste, get into the properties of that paste. And you draw it any two-dimensional layer you want. Then you move the machine up, and you draw another layer. And layer by layer, you'll have a ceramic part that is made of ceramic paste, essentially. So the paste has particles in it and some solvent. So what Robocasting is, this particular method, is layer manufacturing via extrusion. With the important thing is that it's a concentrated, very high solid, fine particulate paste that is now carried in some volatile solvent, like water or alcohol or ketone. And then during the deposition process, the removal of that solvent, just a little bit, will transform the paste into a solid-like state. So we're not curing the ceramic by freezing or by laser sintering or anything like that. We're quote, curing it by just changing the solids loading a little bit and changing the rheology. So as a result, when we make a part of ceramics like this, the part is near net shape, whatever we design, but it's not near net size, because now we do have to dry it, we have to put it in the furnace so that it densifies and gives it the strength and properties that it wants to be. And that's important, because a lot of the 3D techniques now for plastics and metals are near net shape and near net size. We have to factor in shrinkage when we do it. So that might be a drawback in some sense, but the advantage is that this process is extraordinarily fast compared to other 3D printing techniques. And the size of the bead or the extrude that we can make is on the order of 0.1 millimeters to about 4 or 5 millimeters in size. So how does this work? Well, you have to have 3 criteria for your starting ceramic paste. It has to be able to flow through a small orifice at a modest shear rate, modest pressure. And then when it comes out of the orifice, it has to set up into a non-flowable mass so that it doesn't just spread over it. But most importantly, once you put another layer on top of it, it has to be able to accept those multiple layers without defects and have them meld together. Again, without deforming and changing shape. So my advisor in graduate school was this Professor Bill Manazza, and he had an interesting way of describing these kinds of colloidal systems that isn't fundamentally correct, but as a tool for ceramic processes, I think it's underlooked and can be used in a great way. So I'm just going to take a minute to describe it. In a typical phase diagram for molecules, let's take water as an example, what you get, whether it's a gas or a liquid or a solid, is dependent on the pressure that the gas molecules are at or the temperature. So at high temperature and low pressure, you're going to have steam. At a lower temperature and a higher pressure, you're going to have liquid. And then at very high pressure or very low temperature, you're going to actually have ice and crystal. And the molecules behave in that way, where there's more repulsion between the molecules in this state than when they're attracted. The molecules are attracted in this state. So if you apply the same concept to particulate systems, colloidal particles in particular, you have a situation where you can describe ceramic processing. So we got the interparticle force, how the little particles repel each other, versus how dense they are, versus how many particles you have within your water system or your solvent system. Now, when we do slip casting, we learn on slip casting here, we make sure that the particles are fairly repulsive, and that the density is fairly low in the slurry, say 30 volume percent solids. Now, to turn that into a solid, now you're starting to just a liquid, to turn it into a solid, what you do is you take the water out of that slurry, you put it in contact with plaster, the plaster sucks the water out, and that essentially increases the density and pushes you into a solid regime. And when you're doing extrusion, you start out with a flocculated state, where the particles are all attracted to each other, and the particles actually form a network, which is now flowable in plastic, but it's still a network of particles at the bottom of strained water. So now, this is a pliable material, and you can extrude it, but it's already in a solid state. Now, when we do ceramic processing, we learn ceramic processing, all the different things. Typically, you're taught to work in this area or in this area, but this in-between area where things are sort of semi-plastic and hard to control, you're taught that's a hard place to work, let's stay away from that processing area. So, in those areas, it's too thick to slip cast, or too fluid to extrude. But that's exactly where we need to be for Robocasting, turns out. And one of the possible ways to get there is by using what's called polyelectrolyte stabilization. So imagine this is the surface of some ceramic particle. We put these little fuzzy, highly charged fuzzy molecules on the surface. We absorb them on there. And now this becomes a little bit of a barrier where we can control the repulsive force between other neighboring particles. And this is what my graduate research is on in that paper that Bill was talking about, that apparently is used quite often in ceramic processing classes. So back in 1988, somehow this paper gained some traction, and it's, it's very rewarding to know that it's being used in classes here and in classes around the world. So what that means is that depending on the pH and how much of this molecule you add to the system, you can control this repulsion between the particles. And we can tailor, well, actually, let me address this second. I was told that I had to do this. So, Dr. Carden says that all the students should take a picture of this slide right now, so get your iPhones out. And if you can answer this question, you'll get some, based on using this ability, you can get some extra credit. So, you got to figure out how much dispersant you would need at a pH of 8 to disperse a 20 volume percent aluminum suspension for particles that have 1 micron in size. Okay, back to the topic at hand. We got some, we're using polyelectrolyte stabilization to try to work closely to that semi-plastic regime. And then with just a little bit of evaporation, so we can have a pseudoplastic, pliable slurry inside the syringe. After deposition, with just a little bit of evaporation, we increase the solids loading just enough to make this material now behave like a solid, even though it's still totally wet. So from a standpoint of viscosity, what we're doing in the syringe is we're working with pastes that are very close to this solids loading where the viscosity is So in this case, it's pseudoplastic and very pliable. In this state, it's dilating, and dilating is a situation like wet sand on a beach, where everything's wet and saturated, but if you were to smack it, it feels like cement. It makes it more like a solid. And that's what we're doing. So after it comes out, there's a little bit of evaporation, and living in Mexico with a humidity of about 10%, you can get this transition to occur very, very quickly. So from a rheological standpoint, what you're looking at from a shear stress versus shear rate curve is in the tube, you're in a pseudoplastic state with a yield point, with just a little bit of drying and transition to a dilated state. Where the more stress you put on it, the more the material is going to resist movement. And if you keep this pseudoplastic to dilating transition in sync as you're building, this is a cross-section of a wall you build. If you keep that dilating transition in sync with what you're building, then this becomes strong enough platform that you can build more on top of it. So if you were to build too fast, you would eventually overcome the yield strength on the bottom, and the material in the part would slump. If you were to build too slowly, then these layers would meld together to get cracking. So you have to find the right situation so that you can keep this transition in sync with your building rate. And when that happens, you can make, in the case of 1999, you can make cool, useless parts. Made a lot of cool looking things using the technology, but it was unclear what this really would be used for. And that was about the time at San Diego National Labs when funding ran out on the project. It was sort of a little bit before its time. And so this technology that we developed, we felt so good about, was going to be put on the shelf. So that's when I started trying to figure out what can I do with this commercially, and negotiated with Sandia to start exploring other commercial applications for this technology, because none of the big companies were interested in investing in it. And we eventually found that we could make some sort of cool, useful products. Not terribly high market, but here's some examples of making crucibles that have a thermocouple tube built into it so that you could do macroscopic PTA for experiment. Here's an X-ray diffractometer hot stage that was being supplied for people instead of using the platinum ones that cost thousands of dollars to skip these ones. So there's some sort of cool, useful things to do with it. And another area that is like that are all the consumables used for thermal analysis, either DTA or PTA, all these little cups. We can stick those out for a fraction of the cost of what the manufacturers currently sell them for. We actually now on our website we actually have a little store now where you can sort of buy this stuff. But the other thing that Robocasting has the capability to do, which might have commercial relevance, is making composites. So you can make composites by either making a preform with just one material and then infiltrating the second material. Or you can use two discrete materials where you can put like an electronic circuit buried into some other material. Or you can have a fugitive material that then is burnt out so that you can make channels inside the cover. Or you can take it further and you can have controlled ratios of multiple materials. Here's an example where we went from 100% silicon nitride on this layer and then functionally graded this material with 100% tungsten on the top layer. So silicon nitride and tungsten you could never co-fire just side by side, but by doing a functional grading, you can co-fire these. Now you go from 100% ceramic to 100% metal in one operation. We took the technology further and made it so that you just don't build on planar surfaces, but you can also build on non-planar surfaces. And you can, again, you can deposit on non-planar surfaces, and we demonstrated with you electronic materials and ceramics and a bunch of pre-existing parts. And we can do precision printing of electronic materials. And the list of materials that we demonstrated were all sorts of oxides, nitrides, carbides, regular thick film case. We can do several metals, a bunch of different composites, and we can also do chocolate peanut butter. Those are usually the most popular. So let's look at the characteristics, though, and some of the realities of this situation. We are putting this down bead by bead in layers, and no matter what you do, you're going to have some microscopic defects between the layers, but you're also going to have this irregularity on the surface. This irregularity is going to scale up with the size of the bead that you deposit. So typically, on the order of, what do we got, about 15% of the diameter of the bead is going to be your roughness. So if you're working with really small tips, really small nozzles, 150 microns, yeah, you can get really fine parts, but it will take you forever to build that part to make 150 microns at a time. Or if you want to go to a bigger bead and build that part in one swipe, you can do it, but the drawback is going to be that a lot of roughness. And similarly, the dimensional tolerance that you have, both in height and width, is going to be related to the size of that bead, which is going to take away from your build speed to try and get something really smooth. So there's some things that it's just not going to be good for. The other thing, like I alluded to, is that you're going to have microscopic defects between the layers. So what we did is we tried to see how bad of a polymer would be by looking at the flexural strength of bend bars versus the processing method, with more of the traditional ceramic processing techniques by pressing, isopressing, and slip casting. Slip casting typically with the highest strength. And what we found out is that with the Robocast thing, it's a lot like composites where you have directionality based because of the micro defects between the layers. So if you break the part lengthwise to the build direction, you can get strengths comparable to slip casting. But if you start breaking in directions perpendicular to your build, then all these little defective areas come into play when you try to bend that thing, and you'll actually reduce the strength by about 20%. So that's going to be a reality that if you want to try to use these for advanced ceramics and really high push the limits of the material, this probably isn't going to be the best way to go. You're probably going to have to hot press and machine or something like that. The other thing to take into account is that the build time, so in this case, the time to build 1 cubic centimeter of material, that needs to be on the order of a minute or preferably even less to be commercially relevant, economical enough so that you can compete with other ceramic processing techniques as a minimum. And if you look at the building capabilities for Robocasting, it's related to the table speed, how fast you're depositing, but it's also inversely related to the square of the diameter. So the smaller you go, the smaller tip size you go, the build time goes exponentially up. And now it takes you out of the range of being economical. So it turns out that where we can fit and still have adequate build times is on the order of about 400 microns and up. So that limits some of your utility. So I think what I want to leave you with at this point is that it's a versatile tool, but there's some inherent limitations. The surface roughness, and that it's not near net size, it is near net shape, you can have to deal with simply integers. So what's the niche to this? Well, it turns out it's particularly suited for components that can tolerate appreciable dimensional variance, but not be made by a traditional method. So something where we can make some sort of structure that has some sort of performance that outweighs any detriment to making it cheaper. Okay, and it turns out, and one that doesn't have to be high dimensional tolerance. And it turns out it's something that is in that niche of these porous lattice structures. So let's look at those in more detail. If you get the rheology right, you can actually build these lattice structures in one operation without requiring any support material. This material just spans this previous layer, and you can make these lattice structures. Now, the lattice structures, we're looking at them as replacements in some niche applications for reticulated foams. So reticulated foams have been around for 30 plus years, where they'll take a sponge, coat it with a ceramic material, and then have a replica of a sponge, but now it's a ceramic sponge. And one of the best companies in the world doing that was started right here in Alfred, is still here in Alfred, High Tech Ceramics. controlled pathway that might have some benefit for some applications. So one of the things with reticulated foams, like I said, they work well. They're used, millions of them are used a year, and they work very well for most circumstances. But there are some problems or areas where it could be improved. You see these areas here where some of the pathways are clogged, and that it's made up of very small struts, and sometimes these struts can break off. So if you're trying to use this as a filter, or if you're trying to use it as a catalyst support, you don't want that ceramic material going downstream, so it can be a problem. The other thing is that they are very randomly structured. So if we did a quick study to just look at flow rates through typical reticulated foams and through our lattices, and the one thing, we can tailor the flow rate exactly to what we need it to be, and it's reproducible part after part after part. You also can make a structure in such a way that you can create a bunch of turbulence as flow is coming through here in this region, and then on the entrances or the exits, you can make it so that you actually encourage laminar flow on the exit, so you don't have a bunch of craziness going on the outside. So you can do whatever you want with these lattices to fit a particular application. This is an application showing using a lattice structure for filtering molten metal. This is a model that was done. And you can see that we're creating a bunch of turbulence, hopefully collecting a lot of slag and impurities in here, and then it comes out, it's nice and laminar, so it goes into the mold nice and clean. And you can also do graded porosity, where we want to trap big things first, and then finer things as we go through to increase the capacity of filter you use at all in one operation. And now we've gone to starting to make designs that have radial filtration, so filtering from the inside out or the outside in. And thing is though, okay, we can make all that stuff, but the time frames and trying to be even closely competitive with reticulated foams is impossible. The only way you can do it is if you start doing things in parallel. So say it takes, for instance, 10 minutes to build a part, and that's not going to cut it from an economic standpoint. But if I can make 10 parts at a time, now I'm down to a minute. If I can make 20 minutes, now I'm down to 30 seconds. So that's what we're working on now at our company, is trying to scale things up. So here's sort of a real-time situation of building a part. Like I said, we can scale things up to make things in parallel. And it actually is turning into a real product. So we've got lattice filtration, our logo, and we're making all sorts of these structures. And most recently, we got an NSF grant to start looking into building larger filters. This one's about 6 inches tall. This is in collaboration actually with Cesarano, which is a company that started here at the incubator in Alfred. And we're trying to use microwave technology to see if we can make that more economic. So, when we started out in 2007, we were making just a small amount, and each year we've grown. This is actually an old slide, and we're now to the point where we're making over 1 million filters a year. Our capacity's grown from 200 a week to over 20,000. So the other thing, though, that these structures could be used for, the exact same structure, is for catalyst supports. So like catalytic converters in the car are made out of antenna cones with straight through channels. In this case, we can make a lattice structure so that the reaction rates can be increased because of the tortuosity that you build into it. And I'll just mention that we can change the surface area by changing the rod size and spacing between the rods to whatever it needs to be. And I'll try to quickly show you that this is a comparison between an oxidation reaction where we convert carbon monoxide into carbon dioxide using a platinum catalyst. So a platinum catalyst on this honeycomb structure. You can imagine as the gas is flowing through here, in order for the reaction to occur, that gas has to get to the surface. So it's all diffusion related. So however long it takes for that gas to get to the surface, that's going to depend on the reaction rate. That's going to control the reaction rate. So it's imagine if you have a water going through a hose. If you put that velocity up really high, the water in the center of the hose is never going to actually get to the wall. So you'll never be able to complete the reaction. And that's what we did here. We turned the reaction rate, we put the flow rate up high enough so that the reaction actually couldn't occur totally within the honeycomb because it was going through a straight-through channel. But the exact same conditions with the exact same amount of catalyst and a Robocast has, we can get that reaction to go all the way to completion. So essentially what we're doing is by using this structure, we're increasing the mass transfer coefficient and getting rid of that limitation. And the same thing occurs when we're trying to combust methane, where we can reduce the combustion temperature of methane about 200 degrees, which means now we can combust methane at a low enough temperature that we don't produce NOx and put pollution control over the world. We've taken a step further and made lattices that actually can heat up with some voltage, and those are being looked at for diesel particulate traps. Also to make braided structures to trap a flame below the surface for infrared heaters. Just an example of more catalyst supports out of different materials. And if I've got time, okay, about 2 minutes. I'm going to go through a thing here for using the same technology as lattices for bone scaffolds. So it turns out that we can make a bone scaffolding out of hydroxyapatite. We can make it have the same properties as natural bone, so that it's machinable. And it turns out that the gaps between the materials and the porosity within the material are such that you can grow natural bone into the structure. The natural bone is just tricked into thinking this is an area that needs to be healed, and all the blue is natural bone growing between the struts and the hydroxyapatite lattice. And we did testing on goats, and it worked very well with new bone being grown within 8 to 12 weeks. So a quick summary on this is that we've got limitations in the process. It's not the be-all, end-all, but it does have real commercial utility for catalyst supports and filter structures in labware. And as far as I wanted to try to give, especially the young engineers, a little touch of commercial business experience. I started out as a scientist with an idea, in the laboratory, and we sort of took it to the demonstration level, and then actually tried to turn it into a real business. And we were featured on the Ceramic Bulletin here in April. But this is how it started. In the year 2000, trying to figure out if there was a commercial niche. Our world headquarters was our garage. And I was there for 6 years. My wife can attest to being out there all hours of the night. In 2007, we actually we figured out something to do with it. We got a license agreement with Sandia. We turned it into a LLC, and we moved into a warehouse, started from scratch. There she is, on the floor. This was our place in 2007, about 1,700 square feet. And then we had to start doing everything, right? When a small company, you have to clean the toilets, you have to go do the marketing, you have to build the products, you have to try to do everything at that point. But it's been successful over the past 7.5 years, and we just recently bought a new facility and remodeled it, moved in. We now have about 6,500 square feet of space with furnaces and multiple. I talked about doing things in parallel, doing things many at a time, and making things commercially relevant. So here's what I want you to do today. If you're an engineer that has an ambition or an entrepreneurial spirit to you, I want you to understand a couple things. First of all, the technology must be solid. You have to have something that's real. People will see through it if it's not. But in reality, the technology perhaps maybe 10 or 20% of the business at most. You have to understand how to turn it into something that somebody's willing to pay for. And when I mean that, so it sounds intimidating. And all the business experts are going to tell you, you have to go out and get venture capital, and you have to have a business plan, and you have to do all this stuff. And they'll try to make sure that you have investors and reduce your ownership. And that can be fine, but what I'm telling you is don't be intimidated by quoting to these experts. I'm telling you that engineers can learn everything you need to know about business 10 times easier than somebody in business can learn. So take your time, learn what you need to do, talk to a lot of people that have done it before, but you can do it. You need to understand the weaknesses, though. There's a lot of engineers that just
You'll know very quickly whether this is going to work or not. In our instance, if after a year or two on the marketplace, if big companies start trying to take you out or people start trying to infringe on your patents, you know you got something. If nobody gives a damn, you might as well close our shop. And keep in mind that the highs are higher as far as emotionally and the lows are lower. You feel like you think you're your own boss, but you're not your own boss at all. You're better off working for somebody who you think you're going to be your boss in a small business. Your boss now becomes the customer. Your boss becomes the insurance people, becomes the lawyers. But more importantly than that, you become your boss becomes your employees, especially in a small business situation where these people took a gamble and work for us. And you feel such an unbelievable obligation to fulfill their livelihood, for their families, that you have to take that seriously. Everyone gets paid before you get paid less. And you have a responsibility to try to honor these people for taking the gamble to come with you. And that's a big thing. And more importantly for a small business, IP, intellectual property, and agreements that you make with companies are totally worthless. They're not worth a piece of paper to spend it on unless you can defend it. So unless you get the money back into the family, whatever you do your IP is, you might want to consider keeping trade secrets and having that leverage that you can make something that nobody else knows how to make. Keep that in mind. Leverage is everything in making these deals. The better you don't have any leverage on somebody else when it goes on. And the bottom line is regardless, even if it doesn't work out, even if it doesn't work out 2 or 3 times, if you've got that ambition, it's worth it. You learn so much, and even if you fail, and even if you still ultimately fail, I'm really glad I'm done. I just want to leave you that message. Thank you very much for your attention.
Thank you so much for a wonderful, wonderful talk. I have to say this next week is here feedback I have heard in our seminars. And I'll tell you why. For the engineers out there, every one of our engineering majors can relate to what we talked about. We talked about mechanical engineering, fluid mechanics, we talked about other technologies used for renewable energy. We talked about how it's used to drive engineering. We talked about how it's used for ceramic and glass engineering, materials engineering. It was fantastic. The design part and the business part. So any questions? Any questions? You may not be getting questions from some students in classes. So I think it's a secret to follow, not asking questions. So let's take one good question. If there are no further questions, thanks to everyone for joining us. See you later. Want to talk down in the room?